Now I'm going to demonstrate how I would work a problem involving the combination of resistors in series and in parallel. Here I've drawn a circuit that has been presented to you in class, and I'm going to go through how I would work this problem. We have a 500 milliamp or 0.5 amp current supply that's supplying power to this entire circuit comprised of 5 different resistors. In this problem, we're asked to find 2 different parameters. First of all, we're asked to find the voltage that's developed across resistor 3. And we're also asked to find the power that's dissipated by resistor R5. Okay, so we want the voltage developed across this resistor and the power dissipated by this resistor right here. So we can use the concept of equivalent resistance to analyze this entire circuit. Ultimately, what we would like to do is to reduce this circuit to an equivalent circuit comprised of 1 current supply and 1 equivalent resistance. So to do that, we're going to have to identify the resistors that are in series and parallel with each other. Remember that series elements are elements that have the same amount of current flowing through them, or see the same current flow, whereas parallel elements see the same potential difference or the same voltage across them, not necessarily the same amount of current. Often what you're going to do with these types of problems is need to look at the extent or the extreme portion of the circuit, the farthest out portion of the circuit. So I'm going to begin this problem by looking at resistors R2 and R5. And I see that both of them are in series with each other because the current that flows through R2 must also flow through resistor R5. From class, we know that since R2 and R5 are in series with each other, we can get the equivalent resistance of the 2 series resistors by adding their resistances. Right, so we have a 60 ohm resistor plus a 100 ohm resistor, which gives us a total equivalent resistance of 160 ohms. So now what we've done is we've reduced this circuit a little bit into a circuit that is now looks like this, where this is still R3, R1, R4, and this is the equivalent resistance that we just determined, R2 and 5. Looking at this diagram, we now see that the same amount of current will not flow through resistor 4 as it will through the resistance of 2 and 5 combined. But because they are connected together at each end, we see that they will share the same potential difference. So therefore, resistor 4 is in parallel with resistor 2, 5. I can combine those into an equivalent resistance by adding them in parallel. So R4 is in parallel with the equivalent resistance 2 and 5. So I can come up with the equivalent resistance of R2, 4, and 5 together by using the equivalent resistance formula, which is 1 over R2, 4, 5 is going to be equal to the inverse of R4 plus the inverse of the equivalent resistance of 2 and 5. All right, so when I do that, I could also write that like this. The resistance of R4 is 640 ohms. Oops, let me try that again. Plus the resistance of the equivalent 2, 5, which we determined up here to be 160 ohms. When I calculate that out, I will wind up with an equivalent resistance of 128 ohms. So now I've created a circuit that looks something like this. Where this resistor is now the equivalent resistance of 2, 4, and 5 combined. Again, looking at this, I see now that resistor 1 shares the same current as that equivalent resistance R245 that we just calculated here. So R1 is now in series with R2, 4, and 5. So I can come up with the equivalent resistance of 1, 2, 4, and 5 all combined by adding them together. R1, 2, 4, and 5 is going to be equal to the resistance of 1 plus the equivalent resistance of 2, 4, and 5 combined, which is 72 ohms plus the 128 ohms that we just calculated, and that gives me an equivalent resistance of 200. Moving on from there, what we have now done is created a circuit that looks like this. R3 in parallel with R1, 2, 4, and 5. These two elements are in parallel with each other because they do not see the same amount of current flow through them, but they do see the same voltage potential across them. So again, we can come up with the equivalent resistance of these two resistors that are in parallel with each other using our parallel addition formula. So the equivalent resistance of all of the resistors in the circuit will be given by this formula. When I fill in those numbers, the resistance of 3 from our original example was 300 ohms. And the equivalent resistance that we just calculated for the 1, 2, 4, and 5 combined was 200. And when I calculate that out, I should get an equivalent resistance of the entire circuit of 120 ohms. So I've succeeded now in reducing my circuit to a circuit that has one equivalent resistance of 120 ohms provided with a current of 500 milliamps. Now that I have that information, I can use the current supply and I can use Ohm's law to calculate the potential that's developed across the entire equivalent resistance. So using Ohm's law, I know that the voltage is going to be the current through the resistive element multiplied by the resistance itself. In this case, I'm given that I have 500 milliamps of current, which is the same thing as 0.5 amps, multiplied by the equivalent resistance, 120 ohms, which means that 60 volts worth of potential is going to be developed across this entire equivalent resistance. Now what I need to do is I need to re-expand my equivalent circuit so that I can determine the voltage and the current across all of the elements in the circuit. So right here across the power supply, we have 60 volts of potential that has been developed. If I now start to expand my circuit again, I know that R3 has 300 ohms of resistance to it, and the rest of the circuit that it is in parallel with, I now know that R1, 2, 4, and 5 has an equivalent resistance, because I calculated that before, of 200 ohms. Because these two elements are in parallel with each other, I know that they will share the same potential or have the same voltage across them, but they will have a different amount of current flow through each of them. So I will call the current flow through R3 IR3, and I will call this the current flow through the entire equivalent resistance. Based on Kirchhoff's current law, we know that the 0.5 amps that's supplied by the power supply needs to be equal to the current that leaves through both resistor R3 and this equivalent resistance. So it needs to be IR3 plus the current leaving through that equivalent resistance. Okay. All right, using Ohm's law, we can calculate the total amount of current that goes through resistor R3. So the current through resistor 3 is going to be equal to the potential across resistor 3 divided by the resistance of R3. From here, we calculated that the potential is going to be 60 volts. And we know that the resistance of R3 is 300 ohms. So therefore, we know that 0.2 amps, or 200 milliamps of current must flow through R3. If 200 milliamps of current flows through R3, and whatever flows through R1, 2, 4, and 5 through that equivalent resistance must sum to half an amp, we now know that what flows through the equivalent resistance must be 0.3 amps. All right. From that, what I'm going to do is I'm going to expand my circuit yet again. And I know that along this leg, from my previous calculations, that R1 is 72 ohms, and R2, 4, 5 has an equivalent resistance of 28 ohms. From my previous calculation, I know that at this node we have 60 volts worth of potential relative to ground, or relative to some zero voltage reference right here. And I know that through this path there must be 0.3 amps worth of current. Again, using Ohm's law, I can now determine the potential that's developed across R1 and R2, 4, 5 equivalent. So I'm going to go directly and calculate the voltage, or the potential difference that's developed across resistor 2, 4, 5 equivalent. Using Ohm's law, I know that the voltage is equal to the current through that resistor times the resistance. I know that the current is 0.3 amps, and I know that the equivalent resistance here is 128 ohms. So that leads me to a potential across that resistor of 38.4 volts. So that means across this equivalent resistance of R2, 4, and 5 with respect to ground, we have 38.4 volts worth of potential developed. Now, if I would have calculated the voltage drop across R1, I could do that in the same way, and I would wind up with 0.3 amps multiplied by the 72 ohms of resistance for R1. And that leads me to a value of 21.6 volts. What that means is that 21.6 volts of potential is dropped as the current flows from 60 volts down to this node right here. So if I take 60 and subtract 21.6 volts, I will wind up with my 38.4. Another way to look at it is that 21.6 volts plus 38.4 volts is going to give me my 60 volts that I had at this node right here. All right, we're getting closer now. I'm going to expand my circuit yet again. I know that this equivalent resistance, R2, 4, and 5, was comprised of R4 in parallel with the equivalent resistance of R2 and 5 combined, which was 160 ohms. And R4 had a resistance of 640 ohms. Again, I know that 0.3 amps must flow into this node right here. R4 and R2, 5 together see the same potential across them, so that means there's going to be a different amount of current flow through each R4 and the equivalent resistance of 2 and 5. Again, I'm going to invoke Kirchhoff's current law. All right, and that's going to tell me that the current through this path of R4 is going to be different than the current through this path. So again, the total of 0.3 amps must be the sum of the current leaving through R4 and R25. I can calculate the amount of current through either path that I choose, and what I'm going to do is I'm going to calculate the current through the R25 path. Using Ohm's law, I know that the potential with respect to ground, or with respect to our 0 volt reference, is 38.4 volts, right here as well as right here. Current is equal to the potential difference across the resistor divided by the resistance. The equivalent resistance is 160 ohms, so when I make that calculation, I wind up with 0.24 amps worth of current that's flowing through this equivalent resistance right here. With that information in hand, now I can expand my circuit yet again. Recognizing that that R25 equivalent resistance was comprised of resistor 2, which had a value of 60 ohms, and resistor 5, which has a value of 100 ohms. I know that through both of these, I have 0.24 amps worth of current flowing. Therefore, I can calculate the potential difference across R2 or across R5. Since R5 is the resistor that we want to know the power dissipation of, I'm going to calculate the potential drop across R5. So the voltage drop across R5 is given by Ohm's law yet again, which is the current through the resistor multiplied by the resistance of that element, which in this case is 0.24 amps multiplied by 100 ohms, which gives me a potential difference of 24 volts. I'm almost there now. I know the current that passes through R5, and I know the potential difference across resistor R5. With that information, I can calculate the power across resistor 5, which is the current multiplied by the voltage. So that's 0.24 amps multiplied by 24 volts. That will give me a total current, that will give me a total power of 5.76 watts being dissipated by resistor R5. Now, alternatively, instead of calculating both the current and the potential drop across R5, right here we already knew what the current was, so we could alternately use a different form of the power equation, which is the power across resistance 5 is equal to the current through it squared multiplied by the resistance. If you take the 0.24 amps, square it, and multiply that by the 100 ohms of resistance, you will also end up with the same value that we calculated here. So sometimes that can be used as a shortcut if you're familiar with the different variations of the power equation. So in conclusion, what we have done is we have taken this original circuit right here. We've reduced all of it into a single equivalent resistance using the equivalent resistance equations. From that, we were able to apply Ohm's law and determine that across resistor R3, using Kirchhoff's current law, we know that 60 volts worth of potential is developed across R3. So that is one of the results that we were looking for. By re-expanding the circuit using Kirchhoff's current law, Kirchhoff's voltage laws, and Ohm's law, we were able to work our way back through the circuit to determine how much current and how much potential is developed across each of the resistive elements. Ultimately then we were able to come up with the amount of power that was dissipated by resistor 5.